Okay, so welcome to my channel once again. And this time we are going to define a group and we are going to show that the fourth roots of unity is indeed an abelian group. Okay, now before going into the details of the solution, let's first identify what are the fourth roots of unity, and then we'll define the group, and then we'll show that the fourth roots of unity is indeed an abelian group. Okay, so the fourth roots of unity are as follows. So the fourth root is represented this way, right? The fourth roots of unity are positive and negative 1 and positive and negative I, where I is equal to the second root of negative 1, right? So see, positive 1 put to the power of 4 is equal to 1, negative 1 to the power of 4 is equal to 1, I to the power 4, I square is negative 1, so I square whole square is actually I to the power 4, which is also 1, and negative I whole to the power 4 is also 1. So these are the elements that we have, positive and negative 1 and positive and negative I. So these are the four elements that we have in our set here, and we need to show that they form an abelian group. Now let's start with the definition of a group, and then we are going to prove the abelian nature of the fourth roots of unity. Okay, so a non-empty set, a non-empty set with a binary operation, right? So we are defining a group, right? So we have got a non-empty set along with a binary operation. Let us say that the non-empty set is G, right? And the binary operation is, let's say, the star, right? So the star and G form a group, right? If the following conditions are true. The first condition that we have is as follows. Let us scroll our page a little bit so that the entire page is available to us. So the first condition, the first property is that for A and B that belong to the set G, these are two elements. It's a non-empty set, right? So it has got two elements. Even if it is a single element, we can take B as equal to A. But whatever it is, we have got A and B in the general case, that if A and B are elements of this particular non-empty set G, then the binary operation A star B is an element of this particular non-empty set G. So this property is called the closure property, CLOSURE. This is called the closure property. The second property, the second condition for this particular pair of set and operation to be a group is that if we have chosen A, B, and C to be the elements of G, again, they can be equal, but without loss of generality, we can assume that all of these elements are non-empty, right? For A, B, C not equal, belonging to G, for A, B, C belonging to G, we shall have A star B star C, right? So you can note that B star C is done first. This operation is conducted first. We'll get some response here, some answer here, and then the operation is conducted with A, right? So this is same as A star B, and that starred with C. So if we just change the order of this operation, the even if we change the order of the operation, the answer remains the same. And this, my friends, is called the associativity of the group, right? Associativity property. So the operation is associative. All right, let's look at what the third property is. The third property is there exists an element E belongs to G such that for all elements A belongs to G, the following holds true. What is the condition that holds true? The condition that holds true is A star E is equal to A, which is equal to E star A, right? So this A here can be any element. Actually, even if it is E, then also it holds true. So there exists an element E such that for all elements of G, including this element E, A star E is equal to A, and E star A is also equal to A. So this is the condition, that the property here that we are defining is the existence of an identity element, right? So this element is called the identity element. Element E is the identity element. Okay. Now, the fourth property, now that we have established that we have got an identity element, we shall see what is the fourth property, right? So the fourth and the last, mind it, this is the last property. So we do not need to worry that there are a lot of properties here, right? Okay. So for all elements of the non-empty set or a group, basically, there exists an unique element unique element B in the non-empty set G, such that the following relation holds. What is the relation? What is the condition that is going to be true? Is that A star B is going to be equal to E, and B star A is also going to be equal to uh, E, right? So E is, as we had previously seen, that E is the identity element, right? E is the identity element, and A star B is going to be equal to the identity element, and B star A is going to be the identity element. And this and B is defined as the inverse of A. So the property that we are defining here is the existence of inverse, correct? So we have got an inverse element for each element of our given non-empty set. So the four properties define that a non-empty set G along with the binary operation star is a group. Okay, now let's show that the fourth roots of unity is an abelian group. All right, so let's look at what our set G is and how can we define our operation star, right? Okay, so let G be equal to our elements 1, -1, I, and -I. Fantastic. Be the set, correct? And let star be the binary operation which corresponds to multiplication of complex numbers. Again, let us remind ourselves that I and -I are imaginary numbers, right? So all numbers that we can see in this set G are the complex numbers, period. Okay, so now let's identify uh, the rules and check whether all the rules are satisfied here or not. So number one, the first condition is that the set should be closed, right? The first is the closure property. So let's see if 1 multiplied by 1 belongs to our set G or not. So 1 multiplied 1 or 1 star 1 to be specific, that is 1 which belongs to G. 1 star -1, right? That is equal to -1, that belongs to G. Then 1 star I is equal to I, that belongs to G, and 1 star negative I is negative I, that also belongs to G. So with 1, everything is closed. Cool. Now let's look at negative 1, right? So negative 1 multiplied by 1 is negative 1, right? That belongs to G. Then actually it is a star over here, right? So negative 1 star of negative 1 is equal to 1. That belongs to G. G contains 1, negative 1, I and minus I, right? So negative 1 multiplied by I is going to be equal to negative I. That belongs to G again, and negative 1 multiplied by negative I is equal to I, that belongs to G. Perfect. We are halfway through in proving that the set is closed under the operation. Okay, so I multiplied by 1, or I star 1 is I, that belongs to G. And then next we have got I star negative 1, that is negative, I, that belongs to G. And then I star, right, I star I is I square, which is equal to negative 1, that belongs to G. And I star negative I, right, that is equal to negative 1, and that also belongs to G. Great. Negative I star 1, that is negative I, that belongs to G. Negative I star negative 1, that equals I, that belongs to G again. Negative I star I is equal to 1, right? Negative of negative 1. So that belongs to G. Okay. And this is positive 1, right? And negative I star negative I, that is negative, negative, positive, positive of negative 1, that is equal to negative 1, right? That belongs to G again. So our set G is closed under the operation star. So we can say that set G is closed under star, the operation star. The first property is satisfied. Let's move to the second property and check whether the second property is correct or not, right? Now, in order to prove the second property, let us not be very explicit in finding the products and all, right? So, what we'll just do is that we'll find out. So, what we'll do is that we'll just take some complex numbers, let's say a plus ib, and another complex number, say c plus id, right? And let's consider yet another complex number. E plus if maybe, right? So and then what we'll do is we'll try to see if this is kind of like if we have the associative property uh, satisfied over here. Okay, so let's see whether it works out or not. And let me tell you, the calculation is going to be a little bit dirty. But then again, like if you want to avoid this calculation, you can always choose to consider the elements and do it. But this gives us a proof that is kind of general proof. Okay, so the associative property, we first do a plus ib multiplied by c plus id, right? Again, this we can replace the star by multiplication over here, and this is operated along with e plus if, right? Again, we can replace the star by multiplication symbol here. So this is ac minus bd as the real component, plus I times bc plus ad as the imaginary part, and this in turn is multiplied by e plus if, right? Okay, so things get a little nasty over here, so but still we'll try to be as vivid as possible. So ac minus bd is multiplied with e, that will give us ace plus minus bde, and then bc plus ad is multiplied by f, and we include a negative in front of it. So we shall get minus ADF and minus BCE. So this is the real component, and the imaginary component is going to be BD, AC minus BD multiplied by F. So that will be ACF minus BDF, and then E is multiplied by BC plus AD. So that will give us plus ADE plus BCE. Okay, let's keep this aside, right? Let's represent that by a star, and let's see what happens if we just reverse the order of of the operation, not the elements. Mind it, right? So a plus ib multiplied by, inside the bracket, c plus id multiplied by e plus if, right? So this is a general proof. This holds true for all complex numbers. Okay, now a plus ib is as it is. Let's return a plus ib as it is, and this is multiplied by, okay, let's see what we have here. So ce minus df, right? That is the real part, plus cf plus de is the imaginary part, correct? And there is an I in front of that, bracket closed over here. And then let's see, let's first identify uh, what are the real parts and then the imaginary part respectively. Okay, so the real part, A is multiplied by CE minus DF. So that gives us ACE minus ADF, right? And then B is multiplied by CF and DE, but with negatives in front because it is a multiplication of one I with another I, which gives a negative 1. So, okay, so B multiplied by CF is BCF, so it becomes minus BCF, right? And then B multiplied by DE gives BDE, so minus BDE, right? Minus BDE. Okay, and then the imaginary part, right? So imaginary part, B would be multiplied by CE minus DF. So BCE minus BDF, right? And there is an I in front outside the bracket, of course. And of course, we have A multiplied by CF plus DE. So we'll get plus ACF plus ADE, right? So this is also something which we'll keep aside, and we'll compare this with the element that we had uh, placed aside previously. So we are just going to circle the terms over here, right? Whichever is common between the previous term and the current term. So I'll use the red pen for doing that. So ACE, we'll first compare the real part. So ACE is and ACE are matching. Minus BDE and minus BDE are matching, correct? Minus ADF and minus ADF are matching. Minus BCE and minus BCF. Oops, so there looks to be a little error over here. Um, but we can resolve it, right? Minus BCF. Okay, let's move, scroll a little bit up, and let's see if we had made a mistake anywhere. So this is BCE, right? BCE, BCE, BCE. Oh yes, so we found out the mistake, right? So this is regarding this particular term BC plus AD multiplied by F. So AD multiplied by F is ADF, that is correct. And BC should be multiplied by F, so this should be BCF. And thus, we have found out the negative BCF term, which is common in both the terms, right? Okay, let's take the blue pen and we'll underline the terms that are common. So ACF is here, ACF is here. Minus BDF is another term which is common in both of them. Plus ADE and plus ADE are common, and plus BCE and plus BCE is common, right? So what do we get here? The result is that multiplication or star is associative in over G. So the second condition is also solved. So now we are left out with the third and the fourth properties, correct? Okay, now let's see. Let's try to identify what is the identity element over here, right? And the identity element over here. So by observation, the identity element is 1, right? Let's see whether it is true or not. So we'll choose 1 belongs to G, right? So what is the condition here? The condition is for all A belongs to G, we have got A star E equals A equals E star A, right? So if we take A as equal to 1, so let's see what happens. 1 star 1 is equal to 1. We know that. Great. And this is 1 star 1 again. Right? Okay. The star here, mind it, is the multiplication that we're talking about. Right? So this is the identity element, and this is the identity element over here. And this is true. No problem regarding that. Let's consider negative 1 belongs to G, right? Okay, negative 1 star 1 is negative 1 multiplied by 1, which is negative 1. And of course, negative 1 multiplied by negative 1 is also equal to my negative 1. So, for negative 1 element, the condition is satisfied. Let's look at I belongs to G, right? So we are checking whether 1 is indeed the identity element or not. So I star 1 is I, because I multiply 1 is 1. And 1 star I, that is 1 multiplied I, is also I. Fantastic. Negative I belongs to G. Let's consider that. So negative I multiplied by 1, which is negative I star 1, is equal to negative I. And of course, 1 multiplied by negative I, or 1 star negative I, is also negative I. So that is also true. So we have established that 1 is the identity element. Okay, now let's look into the fourth property, right? The fourth property says that all elements should have an inverse. So we'll just recall that we had shown that 1 belongs to G is the identity, correct? Now we'll see what are the inverses of each of the elements. Okay, so if we consider 1 belongs to G, we see that 1 star 1, this is the identity element over here, right? Okay, now my bad, it's not the identity element, this is the element here, right? This is the element, this is the inverse, right? So so what we're trying to show here is that 1 is the inverse of itself, right? So the element start the inverse, right? Element start the inverse is same as the inverse start the element, which is equal to the identity. Correct? So the inverse of the identity element is 1 itself. Okay, let's look at negative 1. Negative 1 belongs to G. So we know that negative 1 multiplied by negative 1 is equal to 1, right? Okay, so here this is the element, right? This is the element and this is the inverse. Okay, and 1 is identity element. Again, negative 1, the first negative 1 here is the element, and we start that with the other negative one, which is the inverse. So for negative 1 is the inverse. So it is its own inverse. Okay, let's look at I now. So I belongs to G, correct? So I multiplied I star negative I, okay? So negative I star I is equal to 1, and that is equal to I star negative I, right? So this negative I is going to be the inverse of the element I. Also, negative I belongs to G, has got an inverse as well. So this inverse is going to be I, because I star negative I is equal to 1, and of course negative I star I is also equal to 1. So this is the element negative I, and the inverse is I. So we have got finally the four properties that has to be satisfied for G to be a set, G to be a group. Sorry, my bad. So G comma star is finally a group. Now we need to prove that, remember, we need to prove that G is an abelian group, correct? Now, in order to prove that G is an abelian group, we need to show that the operation on G is commutative. Now, in order to show that this is commutative, we need to prove that for all A comma B belongs to G with, here the condition A should not be equal to B, we have A, B or A star B equals B star A. So this is a condition that we need to satisfy. Okay, let's look into this in a bit more explicit manner. So 1 star negative 1, right? This is equal to negative 1. And we also have negative 1 star 1, right? Negative 1 star 1 is basically negative 1 multiplied 1 in the complex plane, right? So this is also negative 1. So both of these are equal. So and also if we do 1 star I, and that gives us an I, and of course if we reverse the order I star 1, that will also give us I. 1 star negative I equals negative I. The reason that we are doing everything explicitly is because even if we find just one uh, case in which this condition doesn't hold, that will be a contradiction to our claim that this group is an abelian group. Okay, for 1 and negative 1 it is done. For 1 and I it is done. For 1 and negative I it is done. So let's consider now uh, negative 1, let's say negative 1 and I, right? Negative 1 and I. So negative 1 and I is negative I, and I multiplied by, or like the operation is multiplication, negative 1 is going to be negative I again. Negative 1 star negative I is going to be I, and of course negative I star negative 1 is also I. Okay, finally there is just one more pair left of unequal elements. So negative I star I, right? I star negative I rather, that is equal to 1, and I negative I star I, that is also equal to 1. So therefore our group G is abelian, right? So the G is abelian group with operation, with operation, and the operation is star, right? So the operation is basically complex multiplication, complex multiplication. So we have proved that G is a group, and further we have proved that it is an abelian group. So here, my friends, this is the end of the proof. Thank you so much for watching such a long video.